Welcome in the subject of mechanical system design. Today we will discuss about the design of IC engine components. As we know, IC engine it is the mechanical device which is used in the automobile industry as well as another agriculture industry. Also, the IC engine are used. So the internal combustion engine, what are the different components are there that we are already know or discuss. So now we are going to design the that components by using the standard methods as well as considering the properties of the material. So for designing of the IC engine components, so our problem statement is the design of IC engine components for following data. So here the given data is the brake power is given as a 7.35 kilowatt. Then speed of the engine is considered as or given as a 5,000 RPM. Then BMEP, that is a brake mean effective pressure, is a 0.21 megapascal. Then bore to stroke ratio is a 0.909. Then compression ratio CR is given as a 6, and the maximum gas pressure is considered as a 3 Newton per unit square. So for this given data, we are going to design the IC engine components. So the given data brake power is given as a 7.35 kilowatt. Speed in RPM given as a 5,000 RPM. So the N is equal to 5,000 by 2, that is a cycle per minute we are calculated. Then diameter to length ratio is of 0.909 is given. Then N is equal to 2,500 cycles are given. Then 0.25 is a viscosity is given. Compression ratio is 6, and brake mean effective pressure is 0.21. So now first component we are going to design is nothing but a cylinder. So the material for cylinder we consider or taken as a gray cast iron, whose series or designation is FG200. Then the material properties are K is equal to 46 point thermal conductivity 46.5 watt per degree Celsius, and delta T is the temperature difference is the 220 degrees Celsius. Then dimensional cycle, that is the DL ratio, D by L ratio. Bore diameter to stroke length ratio is 0.909. So the L by D ratio will be equal to 1.1. Next will be the brake power is equal to PMLAN eta m upon 60 into 1000. So this is the formula to calculate the brake power. So putting the values, all the values, that stroke length, then area, then speed, then efficiency, 1060 into 4. So we will get the brake power finally. Brake power is also given. We are going to calculate here diameter. So the diameter is come as a 99.06 mm. So this is the diameter for the cylinder. After solving, putting all the values, brake power is given in the problem statement, that is a 7.35 kilowatt. So putting all these value, finally we'll get the bore diameter, capital D is equal to 99.6 mm. So the standard value of bore diameter is considered as 100 mm. Now we know the L by D ratio is equal to 1.1. So from there we will get the stroke length 1.1 into 100. So stroke length will be equal to the 110 mm. Then compression ratio, we know the formula for compression ratio, swept volume plus top clearance upon top clearance. So the L plus L1 by L1. So the compression ratio is given as 6, and stroke length is a 110. So we will get here top clearance L1 is equal to 22 mm. So from this we will get the top clearance. So by using this formula of compression ratio, top clearance we are calculated, which is equal to the 22 mm. The next is the length of the cylinder. So length of the cylinder formula is the stroke length plus top clearance plus piston length LP. So the length of the cylinder LC is equal to stroke length L1 plus top clearance. So the length of the cylinder is equal to L1 plus L plus LP. So then piston length is always equal to the 1.25 the diameter of the cylinder. So assume LP is equal to 1.25 D. We are assuming. Therefore, LC is equal to, we are putting the value of stroke length, then top clearance and the bore diameter value. We will get the length of the cylinder, which is equal to the 257 mm. Now thickness of the cylinder T. As the stress acting on the wall of the cylinders are three types of stresses are there. First one is the circumferential stress due to gas pressure, that is sigma C. Second one is the longitudinal stress due to the gas pressure, sigma L. And third will be the bending stress due to the piston side thrust, sigma R. As the sigma C is equal to P max D by eta T, not eta T, 2T, P max maximum pressure into bore diameter divided by 2 times the thickness. Sigma L is equal to P max D by 4 times T, and sigma R, that is the radial stress, is equal to minus P max, that is nothing but a maximum pressure. And also sigma R is equal to sigma C minus nu into sigma R plus sigma L. So assuming maximum pressure is given as a 3 Newton per mm square and factor of safety is 0.5 equal to 5. Not 0.5, factor of safety is given as a 5. Next, this is a, now we are drawing the cylinder diagram or a flathead cylinder diagram using the dimensions calculated as below. That is a bore diameter 100 mm and thickness we are calculated as a 6 mm. So allowable stress for the cylinder is sigma allowable is equal to SUT upon NF. So sigma allowable is nothing but allowable stress or a permissible stress. SUT is the ultimate tensile strength. And then NF is the factor of safety. So 200 is the ultimate tensile strength of stress and pi is the factor of safety. So the allowable stress is calculated as a 40 Newton per mm square. Now thickness of the cylinder wall is P is equal to P max D by 2 times allowable stress plus C1. So C1 is a 2.3 from the table for the diameter 100 mm. So standard value. Putting the all the value, we will get the thickness of the cylinder is equal to 6.1 mm. Now stresses in the cylinder wall. So once we get the thickness, we can calculate the different stresses in the cylinder wall. So first circumferential stress sigma C is equal to P max into D by 2T. Therefore, putting the value of maximum pressure, then bore diameter and thickness. So we'll get the circumferential stress equal to 24.59 Newton per mm square. Then second one is a longitudinal stress in the cylinder. Sigma L is equal to P max D by 4 times T. So putting the all the value of that is maximum pressure, then bore diameter and thickness of the cylinder, we'll get the longitudinal stress is equal to 12.29 Newton per mm square. Then third one is a radial stress, sigma R is equal to minus P max. So 3 Newton per mm square is the maximum pressure, or we consider the design pressure. So minus 3 will be the radial stress. Then final resultant stress, that is the sigma R, putting the value, we will get the sigma R resultant stress equal to 22.26 Newton per mm square. Next one is the thickness of cylinder flange TF. So TF is equal to, it is always a 1.2 to 1.4 times thickness of the cylinder. So the TF is equal to 1.3 into 6.1. So 6.1 will be the thickness of the wall of the cylinder. So thickness of cylinder flange will be equal to the 8 mm. Next one is the thickness of the cylinder head, that is the TH. So as the material selected for the cylinder head is a grey cast iron, so the TH is equal to K1D under root of P max upon sigma allowable into H. So shape selected is a flat cylinder. So D is the cylinder bore, Then Pmax is the maximum pressure and sigma allowable H is the allowable tensile stress in cylinder head. Therefore, K1 is equal to the constant 0.3 to 0.4 and K1 is the 0.35 taken for flat circular shape. Now the shape of the cylinder is selected as a flat circular. Therefore, TH is equal to K1 will be 0.35. 100 is the bore diameter. Then maximum pressure is the 3 and 40 will be your allowable stress. So the thickness of cylinder head is equal to the 10 mm. So it will come as a 9.58 mm, but it will be equal to the 10 mm. Next one is the number of studs or bolts and diameter of bolts. So the material for stud is alloy steel 40 Ni3 and allowable stress for the bolt is considered as a 70 Newton per mm square. As the number of studs in the range of D by 100 plus 4 is less than or equal to N is less than or equal to D by 50 plus 4. Therefore, by putting the bore diameter values, we'll get the N, that is number of stud, is equal to 6. Next one is the diameter of the stud. As per for the stud material, alloy steel 40 Ni3 is used. Then allowable stress will be 70 Newton per mm square. So the core diameter for stud DC is calculated by using the formula capital D under root of P max by N into sigma into TB. That is nothing but for allowable stress for a stud. Therefore, 100 by putting the value, you will get the 8.45 mm. So the core diameter for the stud is equal to the 9 mm. Next one is a nominal diameter of stud is dB. So dB is equal to dc by 0.84. So the 9 by 0.84 it will become. So the nominal diameter will be equal to the 10.71 for the stud. Next is the nominal diameter for the stud should not be less than the 16. Therefore, dB is equal to 16 mm. Now the diameter of the bolt P circle is taken as a dP is equal to D plus 3 times that bolt nominal diameter. So putting the value of a bolt diameter and nominal diameter, we will get the diameter of the bolt P circle is 148 mm. Then the outside diameter of the flange is DO. So the DO is calculated by the dP plus 2 times the nominal diameter plus 12. So putting the value of dP, that is nothing but a diameter of the bolt with P circle, and dP is your nominal diameter. So putting the value, you will get the outside diameter of the flange, which is equal to the 192 mm. Next is the pitch of the bolt, that is denoted by PBO. So PBO pitch of the bolt is equal to pi dP upon N. So the dP will be 148, that is nothing but diameter of bolt pitch circle, and N is a 6. Therefore, 77.49 will be your pitch of the bolt. So the round figure will be the 78 mm is the pitch of the bolt. Then minimum and maximum permissible pitch are PBO minimum 19 times square root of dB. So that will be equal to 76 mm, and PBO max will be equal to 28 times square root of dB. So that will becomes as a 1112. As the 78 is less than or equal to PBO is less than or equal to 112 mm. Hence the condition of pitch stud is satisfied. So in this way, the different components of cylinders are going to design.